Number 15. The frozen serpents. In December 1974, in the Liaoning province of northeast China, snakes began emerging from hibernation. In winter, in temperatures well below freezing, the snakes crawled from their underground burrows onto the frozen roads surrounding the city of Haicheng, and they died there. Frozen solid on the snow-covered ground, their bodies stiffened in positions that suggested sudden, desperate movement, as if something underground had become more terrifying than the lethal cold above. This was biologically impossible behavior. Snakes are ectothermic. Their survival depends on avoiding exactly the conditions they were crawling into. A snake leaving hibernation in a Chinese winter is a snake committing suicide. Yet dozens of them did it across the region, independently, over a period of weeks. The snakes were not alone. Dogs in Haicheng barked without stopping and refused to enter their homes. Horses became so agitated they injured themselves trying to escape their stables. Chickens refused to roost in their coops and instead flew into trees, where they had never perched before. Rats appeared in the streets in broad daylight, running in groups, apparently oblivious to human presence. Cattle stood motionless in fields, locked in a freeze response that farmers had never witnessed. Chinese seismologists had been monitoring the region since 1974, documenting a series of small foreshocks. However, the animal behavior reports from thousands of citizens added a layer of urgency that the seismic data alone did not provide. On February 4, 1975, officials made a decision that no government had successfully made before or has made since. They ordered the evacuation of Haicheng. Approximately 90,000 people left their homes. Hours later, a magnitude 7.3 earthquake struck the city. Nearly 90% of the buildings were destroyed. Roughly 2,000 people died, most of them individuals who had not evacuated. Without the evacuation, scientists estimate the death toll would have exceeded 150,000. The Haicheng prediction remains the only successful large-scale earthquake evacuation in recorded history. The Chinese government credited a combination of foreshock analysis and the extensive reporting of abnormal animal behavior. The question that haunted seismologists afterward was not whether the animals had sensed the earthquake coming. It was how they had sensed it when every instrument available to human science had not provided a clear enough signal to act on alone. What were the snakes feeling in those frozen burrows that was worse than death by cold? We still do not know for certain. The leading hypothesis involves the detection of changes in the electromagnetic field generated by tectonic stress in the rock below. Snakes are exquisitely sensitive to vibrations transmitted through the ground. Their jawbones rest directly on the Earth's surface and function as seismic receivers. Whatever signal reached them in the winter of 1974, it was strong enough to override the most fundamental survival instinct their species possesses. They chose the cold. Number 14. Dogs on the shore. On the morning of December 26, 2004, dog owners in the coastal city of Galle, Sri Lanka, noticed something strange. Their dogs refused to go for their usual walk on the beach. These were animals that had taken the same route every morning for years. They knew the path, they anticipated it. Yet on this particular morning, every dog pulled away from the shoreline, whined, and would not move toward the water. In the fishing village of Bang Khoi, Thailand, a herd of water buffalo that had been grazing near the coast suddenly lifted their heads in unison, ears rigid, staring out to sea. Then they turned and stampeded up the nearest hill. The villagers, bewildered but trusting the animals they had raised, followed the buffalo uphill. Minutes later, the ocean withdrew from the beach. Then it returned as a wall of water, roughly 30 meters high. The 2004 Indian Ocean tsunami killed approximately 228,000 people across 14 countries. The magnitude 9.1 earthquake that triggered it was the second largest ever recorded by human instruments. The resulting waves traveled across the entire Indian Ocean basin, reaching coastlines within 15 minutes in Indonesia and taking up to 7 hours to strike the eastern coast of Africa. Yet wildlife officials in Sri Lanka reported something that defied expectation. At Yella National Park, the country's largest wildlife reserve and one of the hardest-hit coastal areas, floodwaters surged up to 3 kilometers inland. The park was home to hundreds of wild elephants, leopards, and over 130 species of birds. H.D. Ratnayake, the deputy director of the National Wildlife Department, told reporters in the days after the disaster that no dead animals had been found. Not one elephant, not one leopard, The animals had moved to high ground before the wave arrived. Elephants in the park were seen running inland, trumpeting in distress, before any visible sign of the approaching water. Flamingos abandoned breeding grounds on the coast of India. At Alsane Beach near Phuket in Thailand, dogs ran for the hilltops. In India, a lighthouse keeper observed a herd of antelope stampeding away from the shore. Ravi Korea, president of the Sri Lanka Wildlife Conservation Society, traveled to Yala's Padanangala beach after the disaster. Roughly 60 human visitors to that beach had been washed away. Korea found no animal remains. Along the coast of Cuddalore in India, where thousands of people perished, buffalo, goats, and dogs were found alive and uninjured. Michael Garstang, an emeritus research professor of environmental sciences at the University of Virginia, spent years investigating how elephants may have detected the approaching wave. His hypothesis centers on infrasound, acoustic waves generated by the undersea earthquake at frequencies below 20 Hz, well beneath the threshold of human hearing. Elephants communicate using infrasonic rumbles that travel through both the air and the ground. Their feet contain specialized nerve endings called Pacinian corpuscles that detect low-frequency vibrations transmitted through the earth. The earthquake off the coast of Sumatra would have generated infrasonic waves that propagated across the Indian Ocean basin at the speed of sound in water, roughly 1/500 meters per second. This means the infrasonic signal would have reached Sri Lanka well before the tsunami itself. To an elephant, the ground would have hummed with a frequency that signaled catastrophic geological disruption. The elephants did not predict the wave. They heard the earthquake. Would you have followed the buffalo up the hill? The villagers of Bangkoi did. They are alive because they trusted an animal's judgment over their own understanding of the sea. Number 13. Guardians in the Water. On October 30, 2004, roughly 2 months before the Indian Ocean tsunami, a different kind of rescue was unfolding off the coast of New Zealand. Lifeguard Rob Howes, his 15-year-old daughter Nikki, and 2 of her friends, Karina Cooper and Helen Slade, were on a training swim approximately 100 meters off Ocean Beach near Whangarei on the North Island. The water was clear, the conditions were calm. Then the dolphins arrived. A pod of 7 bottlenose dolphins came at the swimmers fast, which initially alarmed Howes. The dolphins began circling the group in tight, rapid loops, pushing the 4 swimmers together into a compact cluster. Howes, confused, tried to swim away from the formation. 2 of the larger dolphins immediately intercepted him and herded him back. Then Howes saw why. A 3-meter great white shark was gliding through the water roughly 2 meters from where he had been swimming. The water was crystal clear. Howes could see the animal as plainly as he could see his own hands. The shark began moving toward the 3 teenage girls. The dolphins, in Howes's words, went into hyperdrive. They created what he described as a confusion screen, a mass of fins, backs, and tails churning the water around the swimmers so that the shark could not isolate a target. The dolphins maintained this protective formation for approximately 40 minutes until a rescue boat approached, at which point the shark departed. The dolphins stayed close as the group swam back to shore. Howes did not tell the 3 girls about the shark until the following day. He spent the next 3 weeks consulting with marine biologists before going public with the account. Dr. Rochelle Constantine from the Auckland University School of Biological Science confirmed that this type of behavior, while rare, was consistent with documented patterns of dolphin altruism. Ingrid Visser, a marine mammal researcher with 14 years of field experience, noted that similar reports of dolphins protecting swimmers from sharks had been documented in multiple countries. The dolphin rescue raises a question that scientists have debated for decades. Was this altruism, genuine concern for the welfare of another species? Or was it an extension of the dolphins' natural anti-predator behavior, where they instinctively formed defensive circles around vulnerable members of their own pod and simply included the humans because they were there? Dolphins and sharks are natural adversaries. Bottlenose dolphins will attack sharks that threaten their calves, ramming them with their hard, bony rostrums at high speed. A coordinated pod can seriously injure or kill a shark. The behavior Howes witnessed may have been triggered not by compassion for the humans, but by the dolphins' own threat assessment. The shark was a danger to the pod. The humans happened to be inside the defensive perimeter. Yet the dolphins did not simply flee, they stayed for 40 minutes. And they pushed a man who tried to leave back into the protected zone. That detail, the deliberate correction of a human's behavior, is difficult to explain as incidental self-defense. Stories of dolphins rescuing humans stretch back to the 7th century BC, when the Greek poet Arion described being carried to shore by a dolphin after pirates threw him into the sea. Plutarch wrote of similar encounters. Archaeological pottery from ancient Greece depicts dolphins supporting human figures above the waves. These stories were dismissed for centuries as mythology. The incident at Ocean Beach suggests that the myths may have been describing something real. Number 12. The language of alarm. In the grasslands of northern Kenya, African elephants have a word for humans. Not a metaphorical word, not a general alarm signal. A specific vocalization, distinct from all other elephant communications, that means something close to danger, humans nearby. In 2014, Dr. Lucy King of the University of Oxford and the conservation organization Save the Elephants, together with bioacoustics expert Dr. Joseph Soltis from Disney's Animal Kingdom in Florida, published a study in PLOS One demonstrating that African elephants produce acoustically distinct alarm rumbles in response to different threats. When recordings of disturbed African honeybees were played to resting elephant families in Kenya, the elephants fled the sound while producing a specific low-frequency rumble. When recordings of Samburu tribesmen speaking were played to the same elephants, they fled again, but the rumble they produced was measurably different. The distinction between the two alarm calls was not volume, it was not duration. It was a shift in the second formant frequency, the same acoustic feature that distinguishes vowel sounds in human speech. The difference between the elephant rumble for bees and the elephant rumble for humans is comparable to the difference a person produces when changing a vowel in a word. Both calls traveled at infrasonic frequencies that elephants can hear but humans cannot detect without specialized equipment. The behavioral response differed as well. Elephants hearing the bee alarm rumble ran away while shaking their heads, a movement consistent with trying to dislodge stinging insects from around their eyes and trunks. Elephants hearing the human alarm rumble ran away without shaking their heads. The response was threat appropriate. The elephants were not simply panicking. They were communicating specific information about the nature of the danger and adjusting their behavior accordingly. King's research built on earlier work showing that elephants actively avoid beehives in the wild and will flee from the recorded sound of angry bees. Despite their enormous size and thick hides, adult elephants can be stung around their eyes and inside their trunks. Calves, whose skin has not yet thickened, can be killed by a sustained bee swarm. The fact that a 6-ton animal fears a 2-gram insect is remarkable. The fact that it has a specific vocal warning for that insect is something else entirely. King conceded the possibility that the alarm rumbles might simply be emotional byproducts of running, vocalizations produced reflexively during flight that other elephants interpret as threat signals. However, she noted that the acoustic precision of the calls, their consistent production across different elephant families, and their threat-specific associated behaviors all suggest something more deliberate. The elephants may be choosing to produce these sounds. They may be warning each other on purpose. If elephants possess a vocabulary of threat-specific alarm calls, then the boundary between animal communication and language becomes uncomfortably thin. Number 11. The warbler evacuation. In the spring of 2014, a population of golden-winged warblers had just completed a 5,000-kilometer migration from eastern Colombia to their breeding grounds in the Cumberland Mountains of eastern Tennessee. They had been there for approximately 1 week. Territories had been established. The breeding season was beginning. Then, on April 26th, the birds left. All of them. Henry Strebe, an ecologist then at the University of California, Berkeley, had fitted 20 of the warblers with miniature geolocators as part of a study testing whether birds weighing less than 2 nickels could carry tracking devices. The geolocators were light-level sensors that recorded the bird's position based on sunrise and sunset timing. Strebe was not studying storm behavior. He was studying migration routes. When the geolocator data was recovered, it showed something Strebe had never seen before. Between April 26th and May 2nd, the 5 warblers for which the period of interest was fully recorded had reversed course and flown south, away from their breeding grounds, traveling as far as the Gulf Coast. 3 of the birds flew more than 900 miles round-trip. They flew around the approaching storm system, each bird taking a different route, and returned to their territories after the weather passed. 2 days after the warblers departed, on April 28, 2014, a massive supercell storm system swept through the southeastern United States. It generated 84 confirmed tornadoes and killed 35 people. Strebe published the findings in Current Biology in December 2014. He called it evacuation migration, a term that had never been used in ornithology before, because no one had documented this type of behavior in breeding songbirds. The birds had abandoned freshly established territories, the most biologically valuable real estate they would occupy all year, and flown hundreds of miles to avoid a storm that had not yet arrived. The critical detail was timing. When the warblers departed, the supercell was between 250 and 550 miles away. Local weather conditions in Tennessee were normal. There were no changes in barometric pressure, wind, or temperature that would have signaled danger. At the same time that meteorologists on the Weather Channel were beginning to warn viewers that a severe system was developing, the birds were already gone. Strebe suspects the warblers detected infrasound generated by the forming storm system. Severe weather produces low-frequency acoustic waves below the 20 Hz threshold of human hearing. These waves can travel thousands of miles through the atmosphere. Birds, whose hearing extends into lower frequency ranges than human ears can access, may detect these infrasonic signatures and interpret them as indicators of approaching danger. A bird that weighs 9 grams, the weight of 4 dimes, heard a storm that no human ear could detect from 500 miles away and made a decision to abandon the most important location of its biological year. The bird then flew around the storm, navigated back to its exact territory, and resumed breeding as if nothing had happened. No meteorological instrument provided a clear warning at the time the birds departed. The warblers knew before the radar did. Number 10. The grudge holders. In 2006, wildlife biologist John Marsloff at the University of Washington in Seattle conducted an experiment that would change how scientists think about the cognitive abilities of wild birds. He and his students put on rubber caveman masks and captured 7 to 15 wild American crows at 5 sites on or near the university campus. The crows were banded, measured, and released unharmed. The entire interaction lasted minutes. Then the researchers waited. Over the following months and years, anyone who walked through the study area wearing the caveman mask, regardless of their size, age, gender, or walking gait, was immediately scolded. The crows dove at them, squawked loudly, and followed them across campus. A control mask, a rubber face modeled after former Vice President Dick Cheney, drew no response. The crows ignored it completely. They reacted only to the face they associated with capture and handling. The study, published in Animal Behavior in 2010, demonstrated that wild American crows could quickly and accurately learn to recognize a specific human face after a single brief negative experience, and that they retained this recognition for years. Marsloff's team documented consistent scolding behavior directed at the threatening mask for more than 2.7 years after the initial capture event. However, the most significant finding was not individual memory, it was social transmission. Crows that had never been captured, that had never personally witnessed the trapping event, began scolding the threatening mask. They had learned from other crows that this face was dangerous. In a follow-up study published in the Proceedings of the Royal Society B in 2011, the researchers confirmed that anti-predator information about dangerous humans spread through the crow population via social learning. Young crows that were not yet alive when the original captures occurred eventually scolded the mask. The knowledge was being taught. In 2012, Marsloff published brain imaging results showing that when crows were exposed to the threatening mask, their brains activated in the amygdala, a region associated with fear processing in mammals, including humans. The neural circuitry that crows use to evaluate dangerous faces appears to operate through mechanisms similar to those used by the human brain. The fear is real. The recognition is precise. And the memory is extraordinary. University of Washington researchers documented scolding responses to the original threatening mask persisting for up to 17 years after the initial capture. Marsloff was once approached by the United States military about whether crows could be trained to locate specific individuals. His response captured the implication. If a group of crows knew a particular person as an enemy, they would certainly indicate that person's presence the next time they saw him. The crows on the University of Washington campus have been watching you decide whether they are intelligent. They decided long ago. Number 9. The bird that talks to humans. In the wooded savannas of Mozambique's Nyassa National Reserve, a small, drab bird called the greater honeyguide does something that no other wild animal on Earth has been scientifically documented doing in quite the same way. It communicates with humans, it leads them to food, and it has been doing this for at least 500 years, possibly far longer. The honeyguide eats beeswax. It can find bees, nests hidden in the hollows of baobab trees and other tall hardwoods across sub-Saharan Africa. What it cannot do is open those nests. The bees defend them viciously, and the honeyguide, despite its name, lacks the physical tools to break through bark and honeycomb. Humans, however, possess axes, smoke, and a tolerance for bee stings that comes with motivation. The honey inside those nests is intensely caloric and was, for millennia, one of the most valuable food sources available to hunter-gatherer populations. The relationship works like this. A Yao honey hunter in Mozambique walks into the bush and produces a specific call, a loud trill followed by a guttural grunt. In Tanzania, a Hadza hunter uses a complex melodic whistle instead. If a honeyguide is within earshot, it responds. The bird flies down, chattering loudly, and begins leading the hunter through the landscape, flitting from tree to tree, always staying visible, always vocalizing. When the bird reaches a tree containing a bee's nest, it perches nearby and goes silent. That silence is the signal. The hunter begins searching the tree for the hidden hive. In 2023, Claire Spottiswoode at the University of Cambridge and Brian Wood at UCLA published a landmark study in Science demonstrating that honeyguides in different regions of Africa have learned to recognize and respond to the specific calls used by local human populations. When researchers played recordings of Hadza whistles to honeyguides in Tanzania, the birds cooperated 82% of the time. When they played the Yao trill from Mozambique, the same birds cooperated only 24% of the time. In Mozambique, the pattern reversed. The birds responded preferentially to the call they knew. The honeyguides are not domesticated. No one trains them. They are brood parasites, laying their eggs in the nests of other birds, which means young honeyguides are never raised by their own parents. Whatever the birds know about human calls, they learn it on their own, likely by observing other honeyguides interacting with hunters. Earlier research by Wood demonstrated that honeyguides increased Hadza hunters' rate of finding bee nests by 560%. This is not a marginal benefit. The Hadza acquire roughly 8 to 10% of their annual caloric intake with the help of honeyguides. The partnership is a meaningful survival advantage, sustained across hundreds of generations, between two unrelated species that have developed a shared communication system through cultural evolution. The Yao hunters lay out cleaned honeycombs on beds of leaves as payment for the bird's service. The Hadza hide or burn their honeycombs, keeping the bird hungry so it will guide again. The honeyguides cooperate with both strategies. The relationship, in the words of Brian Wood, involves elements of both mutualism and manipulation. Yet the relationship is fading. As farming spreads and store-bought sugar becomes available, fewer people hunt for wild honey. Fewer hunters make the calls. And the honeyguides, one generation at a time, have fewer teachers. Spottiswoode noted that there may be a mosaic of honeyguide cultural variations across Africa that mirrors those of their human partners. A map of disappearing human traditions is simultaneously a map of disappearing bird traditions. Neither species wrote the other's language down. Number 8. The Internet of Animals. In 2016, a magnitude 6.6 earthquake struck near the town of Norcia in the Apennine Mountains of central Italy. The October earthquake was the largest in a sequence that had been shaking the region for weeks, damaging medieval architecture and displacing thousands of people. At a farm near the epicenter, 6 cows, 5 sheep, and 2 dogs were wearing something unusual. Accelerometer sensors, the same type of motion tracking technology used in smartphones, had been strapped to their collars months earlier by a team led by Martin Wikelski at the Max Planck Institute of Animal Behavior in Radolfzell, Germany. Wikelski was not studying earthquakes. He was developing the Icarus system, the International Cooperation for Animal Research Using Space, a global satellite-based network designed to track the movements of wild and domestic animals in real time. The farm animals near Norcia were part of an early pilot study. When the earthquake sequence began, Wikelski and his colleagues had months of continuous movement data from these animals, recorded at 3-minute intervals, 24 hours a day. The data revealed something that no seismological instrument had captured. In the hours before significant earthquakes, all the animals on the farm became unusually active. The cows, sheep, and dogs showed elevated movement far above their normal behavioral baseline. The activity spike began roughly 12 hours before the strongest earthquakes and intensified dramatically approximately 45 minutes before the ground shook. The closer the animals were to the epicenter of the impending quake, the earlier their behavior changed. Wikelski published the findings in the journal Ethology in 2020. He described the scene inside the stables approximately 45 minutes before one earthquake as resembling a stock market crash. All the animals were going crazy simultaneously. The proposed mechanism involves the release of ions from rocks under extreme tectonic stress. As tectonic plates grind against each other before an earthquake, the pressure generates electromagnetic anomalies and releases charged particles into the surrounding air and ground. Animals with sensitive fur, feathers, or skin, and with nervous systems attuned to electromagnetic and vibrational stimuli, may detect these changes before any human technology does. Real-time monitoring data collected from December 2019 onward demonstrated what an animal-based earthquake early warning system could look like in practice. A chip on each collar sent movement data to a central computer every 3 minutes. The system was programmed to trigger a warning signal if it detected significantly increased activity sustained for at least 45 minutes. The researchers received one such warning. 3 hours later, an earthquake struck directly below the stables. The Icarus project launched its first dedicated satellite in 2025. The system aims to track 100,000 animals worldwide, creating a planetary network of living sensors that detect earthquakes, volcanic eruptions, and emerging disease outbreaks through anomalies in animal movement. The ancient art of augury, reading animal behavior to predict the future, is being resurrected for the space age. The irony is that every civilization before ours already knew this. The Romans watched birds, the Chinese watched snakes, the Japanese watched catfish. We are spending millions of dollars building satellite systems to confirm what farmers in every culture on Earth have been saying for thousands of years. The animals know first. Number 7. The Volcano Whisperers. On the slopes of Mount Etna in Sicily, the most active volcano in Europe, a herd of goats did something that volcanologists could not explain. They moved downhill. Not casually, not as part of their normal grazing pattern, but deliberately, decisively, well before the volcanic monitoring stations registered any change in seismic activity that would have triggered an official warning. Martin Wikelski's Icarus team had been tracking the goats using GPS collars as part of the broader animal monitoring initiative. When the team analyzed the movement data against the timeline of Etna's eruptive episodes, a pattern emerged. The goats consistently descended from the upper slopes before eruptions. They moved to lower elevations, positioning themselves further from the volcanic vents, with timing that preceded official geological alerts. They know much earlier than the volcanologists can see on their equipment, Wikelski told the Sunday Times, and they know better how big it will be. The goats' response appeared to be proportional. Smaller eruptions triggered moderate relocation, larger eruptions triggered earlier and more dramatic descents. This suggests the goats were not simply responding to a single binary stimulus, but were processing a gradient of intensity, adjusting their behavior to match the severity of the approaching threat. The proposed mechanism is the same one hypothesized for the Italian farm animals during the Norcia earthquake sequence. Tectonic and volcanic processes generate electromagnetic disturbances and release airborne ions from fractured rock. Goats, with their sensitive hooves, fine body hair, and nervous systems evolved for life on rocky, seismically active terrain, may detect these signals through a combination of ground vibration, electromagnetic field changes, and chemical sensing. Etna has been erupting for at least 500,000 years. Goats have been living on its slopes for millennia. The relationship between the two is not coincidence. It is adaptation. The goats that failed to read the mountain did not pass on their genes. The goats that descended in time survived to reproduce. Over thousands of generations, the ability to detect volcanic precursors became embedded in the population's behavioral repertoire. Not through conscious understanding of geology, but through the relentless mathematics of natural selection. We monitor Etna with seismographs, tilt meters, gas analyzers, infrared cameras, and satellite radar. The goats monitor it with their feet. And on at least some occasions, the goats are faster. Number 6. The Prairie Dog Dictionary. For over 30 years, biologist Kon Slobodchikov at Northern Arizona University studied a single colony of Gunnison's prairie dogs in the grasslands near Flagstaff, Arizona. What he found forced a fundamental reconsideration of how scientists define animal communication. Prairie dogs produce alarm calls when predators approach their burrows. This much had been known for decades. What Slobodchikov discovered was that these calls were not generic alarms, they were descriptions. Using spectrographic analysis of hundreds of recorded calls, Slobodchikov and his team demonstrated that prairie dog alarm calls encode specific information about the approaching threat. The calls change depending on whether the predator is a hawk, a coyote, a domestic dog, or a human. Within the category of human, the calls change further. Prairie dogs produce acoustically distinct calls for humans wearing different colors of clothing. They produce different calls for tall humans versus short humans. They produce different calls for humans carrying objects versus humans with empty hands. The animals are not simply alerting the colony that danger exists. They are communicating what the danger looks like. Slobodchikov ran controlled experiments in which human volunteers walked through the colony wearing shirts of different colors. The alarm calls varied consistently with shirt color. When volunteers wore identical clothing but differed in body size, the calls varied with body size. The acoustic variations were small, measured in millisecond changes in the duration and frequency of specific call components, but they were consistent and repeatable. The implication is that prairie dogs possess a rudimentary descriptive language. Not language in the full human sense, but a communication system sophisticated enough to transmit referential information about the physical characteristics of external objects. This is not a reflex, it is a description. If a rodent the size of a football can describe you to its neighbors using encoded vocalizations that specify your height, your clothing color, and whether you are carrying something, the question is not whether animals can communicate. The question is how much they have been communicating about us that we have never bothered to listen to. Number 5. The Elephant Infrasound Network. On the morning of December 26, 2004, at Yala National Park in southern Sri Lanka, elephants began trumpeting. They had not been disturbed. No predators were approaching. The weather was calm. Yet multiple witnesses reported that the elephants vocalized in obvious distress and then moved, rapidly and deliberately, toward higher ground. They did this before the tsunami wave was visible, before the ocean withdrew from the shoreline, and before any human in the vicinity had reason to believe that anything was wrong. Not a single elephant at Yala was killed by the tsunami, yet roughly 60 human visitors to the same coastal areas of the park were swept away and drowned. Michael Garstang, who spent decades studying elephant communication at the University of Virginia, has dedicated years to understanding how this was possible. His research centers on infrasound. Elephants communicate using vocalizations at frequencies as low as 14 Hz, well below the 20 Hz threshold of human hearing. These infrasonic calls can travel through the atmosphere over distances of 10 kilometers or more. Elephants also detect ground-borne vibrations through specialized receptors in their feet, called Pacinian corpuscles, which are sensitive to frequencies in the range produced by seismic events. The magnitude 9.1 earthquake off the coast of Sumatra generated infrasonic waves that propagated through both the ocean and the Earth's crust. These waves traveled faster than the tsunami itself. By the time the first wave reached Sri Lanka, roughly 90 minutes after the earthquake, the infrasonic signal had already been moving through the ground and the air for an extended period. To an elephant, the approach of the tsunami was not silent, it was loud. The earthquake announced itself in a frequency that elephants had been using to communicate with each other for millions of years. The elephants did not predict the wave. They heard the earthquake in a language they already spoke. Gerstang has proposed that elephants may function as living seismographs, detecting geological events at distances and timescales that exceed the capacity of many human monitoring systems. If this is correct, then the absence of elephant casualties during the 2004 tsunami was not luck. It was biology. Number 4. 373 BC. The oldest documented case of animals predicting an earthquake comes from ancient Greece, and it is specific enough to qualify as historical record rather than mythology. In 373 BC, the Greek city of Hellas, located on the southern shore of the Gulf of Corinth, was destroyed by a catastrophic earthquake, followed by a tsunami that submerged the ruins beneath the sea. The city was an important religious center, home to a major temple of Poseidon. Its destruction was total. Survivors were few. The historian Aelian, writing several centuries later but drawing on contemporary accounts, recorded that 5 days before the earthquake, all the animals in Helix began to leave. Rats, snakes, weasels, centipedes, and other burrowing creatures emerged from the ground and moved toward the outskirts of the city in broad daylight. The residents of Hellas observed this mass exodus but did not understand its meaning. They watched the animals leave. Then the earthquake came. Thucydides, Pliny the Elder, and other ancient writers reference similar animal behavior preceding seismic events across the Mediterranean world. Pliny noted that earthquakes were often preceded by the agitation of cattle and the flight of birds. These observations were not treated as superstition by the ancient writers. They were treated as empirical facts, patterns that had been observed repeatedly and recorded because they appeared to be reliable. What makes the Helix account significant is its specificity. 5 days. An identifiable set of species, a direction of movement away from the future epicenter, and a catastrophic outcome that confirmed the pattern. If the residents of Helix had followed the rats, every one of them would have survived. 24 centuries later, we are building satellite systems to do what the people of Helix could have done by watching their feet. The rats were already leaving. The technology was there. It was alive, four-legged, and running for the hills. Does knowing that animals have been warning us of danger since before recorded history change how you think about the natural world around you? The warnings have always been there. We stopped listening. Number 3. Sensing the invisible. In December 2019, Martin Wikelski's team at the Max Planck Institute began receiving real-time data from sensor-equipped farm animals near their study site in central Italy. The accelerometer collars transmitted movement data to a central server every 3 minutes, around the clock. The system was designed to flag unusual activity, specifically any period where animal movement exceeded normal behavioral baselines for 45 minutes or longer. In the early weeks of operation, the system flagged an anomaly. The cows, sheep, and dogs on the farm were collectively more active than expected, and the elevated activity had been sustained for well over an hour. Wikelski's team noted the warning. 3 hours later, an earthquake struck the region. The epicenter was directly below the stables where the animals were housed. This was not a coincidence uncovered in retrospect. This was a real-time detection event. The animals flagged something. A timestamp was recorded. The earthquake occurred afterward. The order of events was documented with sensor data. Wikelski has proposed what he calls the Internet of Animals, a global network of sensor-equipped creatures, from goats on Etna to migratory birds over the Pacific, whose collective movement data could be analyzed in real time by machine learning algorithms trained to detect pre-disaster behavioral anomalies. The Icarus system's first dedicated satellite launched in 2025, and the network now aims to track up to 100,000 animals across every continent. The vision is extraordinary. A planet wrapped in a mesh of biological sensors, each one a living seismograph, a living barometer, a living early warning system, broadcasting its position and activity level to satellites overhead. The ancient practice of watching animals for signs of danger, formalized, quantified, and scaled to a planetary level. The cost of the Indian Ocean Tsunami Warning System, the network of ocean buoys and seabed sensors built after 2004, runs between $50 and $100 million per year. Wikelski's animal tracking collars cost a fraction of that. The animals are already deployed, they are already paying attention. They have been paying attention for longer than our species has existed. We are finally building the technology to listen to what they have been trying to tell us. Number 2. The Ancient Contract. There is a pattern in the evidence that most discussions of animal warning behavior overlook. The honey guides do not warn humans of danger. They lead humans toward a resource, and in doing so, both species benefit. The dolphins in New Zealand may not have been protecting the swimmers on purpose. They may have been defending their own pod, and included the humans incidentally. The crows do not warn humans about threats. They warn each other about threatening humans. The elephants are not sounding an alarm for our benefit. They are communicating with other elephants. In almost every case, the animal behavior that humans interpret as a warning is not directed at us. It is directed at members of the animal's own species, or it is behavior driven by the animal's own survival instincts. We benefit from it because we happen to share the same environment, face the same threats, and are observant enough, when we choose to be, to notice what the animals are doing. This is not a weakness in the evidence, it is the most important insight the evidence contains. The natural world is saturated with information that human technology cannot access. The ground hums with frequencies below our hearing. The air carries electromagnetic signatures our skin cannot feel. The chemistry of approaching weather systems is legible to noses 1,000 times more sensitive than ours. We live inside an ocean of data that we are neurologically incapable of perceiving. Animals do not warn us because they care about us. They warn us because they are paying attention to the same world we inhabit, and they are equipped to read it in ways we are not. When we watch them and act on what we see, we are not receiving a message intended for us. We are eavesdropping on a conversation that has been happening for millions of years between species and the planet they live on. That conversation did not begin with us. It will not end with us. Number 1. Why they still try. In the wooded savannas of Mozambique, a Yao honey hunter makes a sound, a trill followed by a grunt. A wild bird hears the call, recognizes it, and flies down. The bird leads the human through the bush, chattering as it goes, stopping at a tree and falling silent when it reaches the hidden hive. The human opens the nest, takes the honey, leaves the wax for the bird. No contract was signed, no treaty negotiated, no domestication occurred. Two unrelated species, separated by hundreds of millions of years of evolutionary divergence, developed a shared communication system through mutual observation, cultural learning, and the slow accumulation of trust across generations. The Yao learned the call from their fathers. The honey guides learned to respond from watching other honey guides. Both species taught their young. This partnership may be thousands of years old, possibly older. Yet it exists only in places where the two species still share space, still need each other, and still make the call. As farming spreads, as sugar becomes cheap, as protected areas are fenced, the hunters stop calling. And 1 generation later, the birds stop responding. A communication system that survived millennia dissolves in a single human lifetime. The cases in this video span 400 years, from the rats of Helesay to the Icarus satellites. They include snakes that chose death over the thing they felt underground, dolphins that held a perimeter for 40 minutes against a predator they could have simply outswum, birds that reversed a 5,000-kilometer migration to avoid a storm their species has no evolutionary memory of surviving, elephants that spoke a word for human in a frequency we needed a laboratory to detect, crows that taught their children to fear a face they had never personally seen. In every case, the animals were responding to the same planet we live on, reading signals embedded in the ground, the air, and the electromagnetic spectrum that our bodies cannot access and our instruments are only beginning to detect. The warnings were never intended for us. They were side effects of animals paying attention to their world with senses we do not possess. Yet here is the part of this story that no one talks about. The fact that we can benefit from these warnings at all requires something fragile. It requires proximity. It requires coexistence. It requires that wild animals continue to live close enough to human populations that their behavior is visible to us. It requires that we maintain ecosystems complex enough to support honey guides and elephants and dolphins and warblers and prairie dogs and crows in functioning populations that exhibit their full behavioral repertoire. Every species we push to extinction is a sensor we permanently remove from the network. Every ecosystem we simplify is a communication channel we close. Every wild space we fragment is a paragraph we tear from a book we have not yet finished reading. The animals are not trying to warn us. They are trying to survive. And in the process, they generate information about the state of this planet that no satellite, no seismograph, no computer model can replicate. Not because our technology is insufficient, because the animals have been calibrating their instruments for 500 million years, and we have been building ours for roughly 200. If you want an early warning system for the next earthquake, the next tsunami, the next eruption, the next pandemic, you do not need more sensors. You need more animals, living where they have always lived, doing what they have always done, speaking in frequencies you cannot hear, to audiences that do not include you, about a world that does not belong to you. And if you are wise, you will listen anyway. If you want to see more videos like this, click the video on screen now and make sure to subscribe.